Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone, welcome to GaN Talk podcast in this new episode where we dive into the latest advancements in GaN reliability and lifetime modeling. As power electronics move into increasingly demanding applications from AI data center to e-mobility and industrial robotics and so on, the ability to predict device behavior under real operating conditions has never been more critical. Today, we explore the newly released Phase 18 reliability report and what it means for engineers designing next-generation power systems. Our special guest is Sheng Zhang, Vice President Reliability at Efficient Power Conversion EPC. Hi, Sheng. How are you? How's it going? Welcome aboard.
Good. How are you?
Good. Everything is good. So today, together, we will bring both deep technical insights and strategic vision on how GaN is reshaping reliability standards in power electronics. So let's start from the big picture. Reliability has always been important in power electronics, but expectations are evolving rapidly. How does the Phase 18 report redefine reliability compared to traditional qualification approaches?
Okay. So let me start from the typical qualification.
Yeah.
Typical qualification produce zero failure, typically out of hundreds or even thousands of parts tested. It does provide some confidence to the customers. However, traditional qualification testing does not address the two following challenges. First is device margin. For example, if the maximum rating of the device is 100 volt, for example, we pass the qualification, that means the parts works well under 100 volt. But what about 101 volt? What happens at 101 volt? Typical qualification does not address that challenge. Second, application relevance. Most qualification tests are based on traditional silicon power MOSFET. GaN are often using applications with different mission profiles, which may not be sufficiently addressed by typical qualification tests. That is why we are developing testing approaches and delivering new test results to address the two above mentioned challenges.
Okay, great. Thank you. So one of the key shifts in the report is the move toward test-to-fail methodologies. So can you explain why test-to-fail is essential for understanding intrinsic failure mechanisms in GaN devices?
Of course. Before me answering the questions, let me first introduce a couple of reliability concepts.
Sure.
I think there are two main failure mechanisms, namely extrinsic and intrinsic failure mechanisms. So what is an extrinsic failure mechanism? In general, failures are caused by defects. These failures usually occur early in operation, after which the chance of failure decreases significantly. It is commonly referred to as infant mortality or early life failures. A second, it's intrinsic failure mechanism. It is also known as wear-out failures, where the failure rate typically increases over time. It means it takes a long time to trigger this failure mode. As you can see, based on the definition of intrinsic failure mechanism, it's highly impractical to test devices for years just to see whether a wear-out failure occurs. Therefore, we introduce this test-to-fail approach, where the devices are subjected to accelerated conditions to trigger wear-out failures within a much shorter time period, say hundreds of hours instead of years. So once failures are observed using this test-to-fail approach, we can perform failure analysis to understand the intrinsic failure mechanisms. So after understanding the failure mechanism, we can develop lifetimes models from first principle, which enables accurate lifetime projection under all application-specific conditions. That is why this test to fail approach is highly critical for understanding and even projection of lifetime for GaN devices.
So understanding wear out mechanisms is fundamental to predicting lifetime and ensuring robust design. What are the key wear out mechanisms identified in GaN amps, and which one are most important, most critical under real operating conditions?
In all the historical reliability reports, we have identified, I would say, 3 main wear out mechanisms. But we have identified more, but I think 3 of them are the most critical ones in real application, which are gate bias, drain bias, and thermomechanical. Among those 3 wear out mechanisms, I would say thermomechanical is probably the most critical one under real world operating conditions for GaN devices. So what is thermomechanical stress? As the name suggests, thermal means it's a temperature related effect. Mechanical refers to a physical or structural deformation. So what happened is that all devices, including GaN devices, need to solder onto a PCB, a printed circuit board. When the temperature increases, materials expands. However, the device and PCB typically expand at different rates. As a result, this mismatch of thermal expansion introduces thermomechanical stress on the solder joint that connect the device to the PCB. When the temperature is constantly changing, the solder interconnect will eventually wear out and break. So I hope that makes sense. So that is, I think, based on our extensive experience working with the customers, that is probably the area we should focus. We focus the most our effort.
Yeah, absolutely. Great. Thank you. So talking about applications, so modern applications like motor drives, LiDAR, high frequency converters introduce highly dynamic stress conditions. So what new insights does the report phase 18 provide on dynamic switching, transient stress, and application-specific reliability?
Oh, good question. There are actually many new insights presented in the new phase 18 reliability report. Since we were on the topic of thermomechanical, let me continue focusing on the thermomechanical stress. In the previous reports, our study focused on investigating thermomechanical wear-out mechanisms induced by the environmental temperature changes, meaning that the PCB and the device experience same temperature variation due to the ambient, due to the environment variation. However, in reality, the GaN devices operate as switches, which can also generate a lot of heat very quickly during switching. However, the PCB temperature remains very close to the ambient temperature because the PCB does not get hot, at least momentarily. So as a result, a temperature gradient is likely to form from the device to the PCB. So we refer to this application-driven thermomechanical condition as power cycle. So the device gets hot, but the PCB is not, right? Instead of the typical thermomechanical, the whole ambient is getting hot and getting cold. So in the phase 18 reliability report, we specifically focus on this aspect of thermomechanical reliability. Maybe back off a little bit. In the previous version, phase 17 reliability report, we did mention and discuss briefly about power cycling. However, in my opinion, it was not thoroughly investigated. Therefore, over the last year, during the course of working on phase 18 reliability report, I believe we did a good job studying this type of power cycling thermomechanical stress condition. And then I think we have developed a pretty comprehensive model to study this with different temperature conditions and power cycling conditions. By the way, the work has also been recognized by the reliability community, as it has been accepted by the International Reliability and Physics Symposium, IRPS, which is the world premium conference on reliability and device physics. So my team actually will be presenting this work at IRPS next week. Interestingly, while we are studying the power cycling over the last year, during the publication of working on the manuscript of the paper, we also identify some additional exciting phenomena. We are currently working on a follow-up study, and we will likely publish the results once it's ready. So there you go. That's
very good. So the report, the Phase 18 report, introduces a dedicated focus on motor drive applications, which present unique and highly dynamic stress conditions. So motor drive systems involve rapid current transients during startup, acceleration, stall events, followed by steady state operation. So how did you emulate these mission profiles in your testing? What did you learn about the GaN robustness in these conditions?
Good question. So this project, actually, we have been working on for probably more than 2 years, actually. Since GaN is proven an excellent solution for motor drive systems in humanoid robots, so our customers have asked us whether we have reliability data demonstrating that GaN is suitable for such application in real life, or application-specific reliability data. So therefore, we first work closely with our humanoid robot customers to define the most common mission profiles, which have not quite adequately addressed by typical qualification tests. So during the process working with our customers, so we define the most common profile is this alternating high current and low current periods with a duty cycle 1 to 4, which may emulate typical startup, acceleration, and stall events during humanoid robot operation. So the next question is that we don't want to develop a whole robots to study this. The next question is that how can we develop a simple reliability evaluation system to study this quickly? Well, in short, we develop a straightforward hot bridge testing system to emulate this low current, high current stress conditions. Well, I say straightforward now, but it wasn't that case back then. So the detailed testing setup, the operating principle are discussed in the section 5.4 in the Phase 18 real report. So now the question is, what did we learn from the testing? So while analyzing the test result, so we were asking ourselves, what are the most possible failure mechanisms under such test conditions? Number one, because it's continuous current and high current, low current. So we think maybe electromigration is a potential concern. So based on that hypothesis, we and also by understanding what's the possible evidence reflecting electromigration, we specifically looking for those evidence. So we actually did not find any sign of electromigration after more than 2,000 hours of testing, but we're still going now. So we crossed that out. The electromigration is unlikely to be an issue in our devices. Second, because following the same concept, power cycling, right? The device is getting hot and the device is getting relatively cold, because high current, the device is getting hot. Low current, the device is not so hot, which is essentially power cycling phenomena. So therefore, solder fatigue is also unlikely reliability risk. So after more than 2,000 hours of testing, we went in, we did a physical cross-section and the solder joint bumps, where we see no clear sign of solder fatigue. So therefore, the current conclusion is that our PQFN package devices are a robust solution for the humanoid robots. However, we're not satisfied with this answer. We'll keep looking. We'll continue our investigation to looking at other aspects and other possible common mission profile to study if there's any weakness in our devices.
Thank you. Great. So this is a great episode that each reliability engineers should listen, should have in the library. Thank you for sharing, Schengen. So in conclusion, my last question. So what are the conclusion? What are the most important takeaways for engineers designing with GaN today, especially in high reliability applications?
Okay. Well, it's a broad question. Let me try to answer in two aspects. First, regarding, because I have mentioned that there are three main wear mechanisms in GaN under real operating conditions, which are gate bias, drain bias, and possibly current stress. So we have developed comprehensive models to model that. I think our conclusion is that if the designers can keep this voltage or current conditions below our maximum rating specified on our datasheet, the reliability risk is fairly low. If there are any unusual or exotic conditions, so we have developed this, you can leverage our test to fail approach. And then we have developed this various lifetime model from first principles, including various input parameters. So we can help you evaluate the associated risk. But still, to conclude on the gate bias, drain bias, and the current stress, we don't believe there is really a reliability risk if you follow the datasheet specifications. I think pretty straightforward. However, regarding thermomechanical related stress, I think this is an area that warrants probably more caution. So we have developed extensive tools and models to help the customers evaluate the risk level relative to the mission profile. If the designers are still unsure, please reach out to our local field application engineers or sales team. We can help address the risk very, very quickly.
Very nice. Thank you. And this brings us to the end of this episode. A big thank you to our guest. Thank you so much, Schengen. It has been a pleasure talking with you.
Thank you.
Stay in touch with the next episode. Thank you and have a good day.